Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that exists both impossibly far away and surprisingly close to home. As you settle in, perhaps adjusting your pillow just right, letting the weight of the day slowly dissolve from your shoulders, I want to share with you one of the most intriguing mysteries that modern astronomy has uncovered. It's a mystery that whispers to us from the deepest reaches of space, carrying messages that have travelled for billions of years just to reach our small blue world spinning quietly in the cosmic dark. You know, there's something profoundly peaceful about contemplating the vast scales of the universe while we're here, safe and warm in our beds. And if you're joining me from somewhere else in the world right now, perhaps it's morning where you are, or maybe afternoon, and you're using this cosmic journey as a moment of meditation in your day. I'd love to know where you're listening from, what time it is in your corner of our planet. Feel free to share in the comments below where you're tuning in from and what draws you to these cosmic mysteries. And if this journey through space brings you the peace and wonder you're seeking, perhaps you'd like to subscribe and join us for more explorations of the universe's gentle mysteries. There's something beautiful about knowing that people all around our world are contemplating these same distant signals, these same profound questions, creating a kind of earthly constellation of curious minds all looking up at the same mysterious cosmos. Tonight, we're going to explore something that at first might seem like it belongs in the realm of science fiction, but I assure you it's very real. We're going to talk about fast radio bursts, mysterious signals from deep space that have been reaching Earth, signals so powerful they can outshine entire galaxies for brief moments, yet so fleeting they last only milliseconds. It's a question that might initially spark skepticism in even the most open minds, but as we gently pull back the layers of this cosmic mystery, you might find yourself wondering something that scientists themselves are beginning to seriously consider. What if these signals, these fast radio bursts coming from billions of light years away, aren't just random cosmic noise? What if they're beacons, intentional signals sent across the vast ocean of space, perhaps by civilizations so ancient and advanced that they've learned to engineer their messages to survive journeys across cosmic time? Now, I know what you might be thinking as you lie there in the darkness. The universe is full of natural phenomena that can seem mysterious at first. Pulsars were once thought to be alien signals when they were first discovered. Their regular pulses so precise that the discovering astronomers initially labelled them LGM, for little green men, but fast. Radio bursts are different in ways that we're only beginning to understand. They come from galaxies so distant that their light has been travelling toward us since before our sun was born, carrying energy equivalent to what our sun produces in decades, compressed into a flash lasting less than the blink of an eye. And perhaps most intriguingly, some of them repeat in patterns that have made even the most skeptical astronomers pause and wonder. As we begin this journey together, let's allow ourselves to embrace both the known and the unknown. Science has taught us that the universe is far stranger than our ancestors could have imagined. We've discovered that space itself can bend and ripple, that time can slow and stretch, that most of the universe is made of matter and energy we cannot see or directly detect. We've learned that there are more galaxies in the observable universe than there are grains of sand on all of Earth's beaches, each galaxy containing hundreds of billions of stars, many of those stars harbouring planets of their own. In such a vast cosmos, filled with such unimaginable possibilities, perhaps the question isn't whether we're receiving signals from cosmic beacons, but rather, why wouldn't we be? The story of fast radio bursts begins quite recently in cosmic terms, though the signals themselves are ancient beyond comprehension. It was 2007 when astronomer Duncan Lorimer and his student David Narkovich were sifting through archival data from the Parkes Radio Telescope in Australia, data that had been collected 6 years earlier. They were looking for pulsars, those spinning neutron stars that emit regular radio pulses like cosmic lighthouses. But what they found instead would fundamentally change our understanding of what kinds of signals the universe could produce. There, hidden in the data like a message in a bottle washed up on a cosmic shore, was a burst of radio waves unlike anything seen before. It lasted just 5 milliseconds, but in that brief instant, it released as much energy as 500 million suns. This discovery, which came to be known as the Lorimer burst, was so unusual that many scientists initially doubted its cosmic origin. Perhaps, they suggested, it was interference from Earth, a microwave oven in the observatory's break room, or a passing satellite. The scientific community approached it with the kind of healthy skepticism that drives good science. But as more telescopes around the world began to detect similar bursts, as the evidence mounted that these signals were indeed coming from far beyond our galaxy, the mystery only deepened. These weren't the regular, predictable pulses of pulsars. They weren't the chaotic static of cosmic storms. They were something new, something that didn't fit neatly into our understanding of natural cosmic phenomena. What makes fast radio bursts particularly fascinating is their combination of extreme properties. Imagine, if you will, a flash of light so bright it could be seen from billions of light years away, but lasting such a short time that if you blinked, you'd miss it entirely. Now imagine that this flash carries information about its journey across the cosmos, its radio waves stretched and dispersed by their passage through the thin veil of particles that exists between galaxies. This dispersion, something astronomers call the dispersion measure, tells us these signals have travelled through vast reaches of intergalactic space, accumulating the fingerprints of their journey like passport stamps from distant cosmic territories. As you drift deeper into relaxation, perhaps feeling your breathing slow and deepen, consider the profound patience required to study these signals. Astronomers might observe the sky for months, their radio telescopes pointed at specific patches of the cosmos, waiting for a burst that might last just a few milliseconds. It's a kind of cosmic meditation, this patient watching and waiting, this careful attention to the subtle whispers of the universe. And when a burst finally arrives, it carries with it information that has been travelling since long before Earth existed in its current form, since before life emerged from our planet's primordial oceans, since before our sun ignited in its stellar nursery. The discovery of repeating fast radio bursts added an entirely new dimension to the mystery. In 2016, astronomers detected something that challenged their assumptions about these cosmic signals. FR B121102, a fast radio burst first detected in 2012, was observed to repeat. Not just once or twice, but hundreds of times. This repetition suggested that whatever was producing these signals wasn't being destroyed in the process. It was like discovering that a message in a bottle wasn't just a one-time communication, but part of an ongoing conversation, a cosmic correspondence that we'd only just begun to intercept. The repeating nature of some fast radio bursts opens up fascinating possibilities. In nature, we see many repeating patterns, from the orbital periods of planets to the oscillations of variable stars. But the patterns in some fast radio bursts don't quite match anything we've seen before. They're not perfectly regular like pulsars, but they're not entirely random either. Some show periodicities that last days or weeks. Others seem to cluster their bursts in ways that suggest underlying mechanisms we don't yet understand. It's as if we're listening to a cosmic symphony but hearing only scattered notes, trying to piece together the melody from fragments that reach us across the vast concert hall of space. As we contemplate these signals tonight, lying here in the gentle darkness, we might wonder about the source of these mysterious bursts. The scientific community has proposed many natural explanations, each more exotic than the last. Perhaps they're produced by magnetars, neutron stars with magnetic fields so powerful they could erase your credit cards from the distance of the moon. Maybe they're the result of cosmic collisions, the death cries of stars being torn apart by black holes, or the birth announcements of new black holes forming from collapsing stars. Each theory has its merits, supported by complex calculations and sophisticated computer simulations. But there's something about the distribution of fast radio bursts across the sky that adds another layer to the mystery. They don't cluster around the plane of our galaxy, as we might expect if they were produced by a population of exotic stellar objects. Instead, they appear to come from all directions, from galaxies near and far, as if the entire universe is participating in this cosmic signaling. Some come from galaxies much like our own Milky Way, spiral arms gracefully wound around bright cores. Others originate in ancient elliptical galaxies, where star formation ceased billions of years ago, leaving only old, red stars to mark the passage of cosmic time. The energy required to produce a fast radio burst is staggering to contemplate. In those few milliseconds of emission, a single burst releases more energy than our sun produces in nearly a century. If we could somehow harness the energy of just one fast radio burst, it would power human civilization for millions of years. This incredible energy output means that whatever process creates these bursts must involve some of the most extreme physics in the universe. We're talking about magnetic fields trillions of times stronger than Earth's, temperatures that make the center of our sun seem cool by comparison, and densities so extreme that a teaspoon of material would weigh as much as Mount Everest. Yet despite these extreme conditions, or perhaps because of them, we can't help but wonder whether intelligence might play a role. After all, if an advanced civilization wanted to announce its presence to the cosmos, what better way than to harness the power of stellar-scale phenomena? We humans have only been capable of radio communication for a little over a century, barely a cosmic eye blink. Civilizations that have existed for millions or billions of years might have developed technologies that seem like magic to us. The ability to engineer signals using the universe's most powerful natural processes as their transmitters. Consider for a moment the challenge of communicating across intergalactic distances. A signal needs to be powerful enough to survive the journey across millions or billions of light years, distinct enough to stand out against the natural radio noise of the cosmos, and brief enough to be practical in terms of energy expenditure. Fast radio bursts meet all these criteria perfectly. They're powerful enough to be detected across cosmic distances. They have characteristics that distinguish them from other known phenomena, and their brevity might actually be a feature, not a bug, concentrating enormous amounts of energy into packets that can pierce the cosmic static. As you continue to relax, perhaps feeling yourself beginning to drift between wakefulness and sleep, imagine the kind of civilization that might create such signals. They would need to think on timescales that dwarf human experience, planning for communications that might not receive responses for millions of years. They would need to have survived their own technological adolescence, overcome the challenges that threaten young civilizations, and emerge with both the capability and the desire to reach out across the cosmic void. Perhaps they're lonely, these hypothetical beacon builders, seeking confirmation that they're not alone in the vast darkness. Or perhaps they're altruistic, leaving markers for younger civilizations to find, cosmic breadcrumbs that say, "You are not alone, we were here. Intelligence can survive and thrive." The search for patterns in fast radio bursts has revealed some tantalizing hints that keep astronomers up at night, though hopefully not you, as you drift deeper into peaceful contemplation. Some bursts show a curious phenomenon called subpulse drift, where the frequency of the radio waves changes in a very specific way during the burst. It's like a cosmic slide whistle, the pitch changing according to mathematical relationships that seem almost too perfect to be natural. Other bursts exhibit what astronomers call bandwidth limitation, where the signal appears confined to specific frequency ranges in ways that natural phenomena typically aren't. There's also the curious case of FRB 180916, which shows a 16.35-day periodicity in its burst activity. For 4 days, it's active, potentially producing multiple bursts. Then it goes quiet for 12 days before the cycle repeats. This pattern has persisted for years of observation, maintaining its schedule with a precision that rivals atomic clocks. Natural explanations have been proposed, involving binary star systems or precessing neutron stars, but none quite perfectly explain all the observed properties. It's as if the universe is playing a game with us, offering clues that lead us deeper into the mystery without quite revealing the solution. The dispersion measures of fast radio bursts tell us stories about their incredible journeys. As radio waves travel through space, they interact with the free electrons scattered throughout the cosmos. Lower frequency waves are slowed more than higher frequency waves, causing the signal to spread out, to disperse, over time. By measuring this dispersion, astronomers can estimate how far the signal has travelled, how many electrons it has encountered on its journey. It's like being able to read the travel diary of each burst, understanding not just where it came from, but something about the path it took to reach us. Some fast radio bursts have dispersion measures that suggest they've travelled through multiple galaxies on their way to Earth. They've passed through the hot gas halos that surround galaxies, through the cosmic web of dark matter and ordinary matter that connects galaxies like threads in a vast tapestry, through the nearly empty voids between galactic clusters where a single atom might travel for millions of years without encountering another. Each burst carries with it information about these cosmic territories, data about parts of the universe we can't observe directly, but can infer from the signatures left on these travelling signals. The polarization of fast radio bursts provides another layer of information, another piece of the cosmic puzzle. Polarization tells us about the magnetic fields the signal has passed through, both at its source and during its journey. Some bursts show linear polarization that rotates as the signal progresses, a phenomenon called Faraday rotation that reveals the magnetic environment of the burst's origin. The amount of rotation can be extreme, suggesting passage through regions with magnetic fields far stronger than anything we encounter in our solar system. It's as if each burst is a probe sent from distant shores to map the magnetic landscape of the cosmos. As we consider these technical details, these measurements and observations, it's easy to get lost in the numbers and forget the profound implications of what we're discussing. Each fast radio burst represents a connection across cosmic time and space. When we detect one, we're receiving information from an epoch when the universe looked very different than it does today. Some bursts come from so far away that their light started its journey when the universe was half its current age, when many of the stars we see in our night sky hadn't yet formed, when the cosmic web was still young and evolving. The host galaxies of fast radio bursts span a remarkable range of cosmic environments. Some are star-forming galaxies, their spiral arms bright with stellar nurseries where new stars are being born in brilliant profusion. Others are quiet elliptical galaxies, where star formation ceased long ago, leaving only the slow cooling of ancient stars to mark the passage of time. Some host galaxies are massive, containing hundreds of billions of stars. Others are dwarf galaxies, cosmic suburbs where conditions might be very different from what we experience in our relatively large Milky Way. This diversity of host galaxies suggests that whatever produces fast radio bursts isn't limited to specific cosmic environments. If they're natural phenomena, it means the conditions necessary to produce them can arise in many different settings. If they're artificial, it might mean that intelligence can emerge and thrive in a wide variety of cosmic neighborhoods. Either possibility expands our understanding of what's possible in the universe, pushing the boundaries of our cosmic imagination. The rate at which fast radio bursts occur is itself a mystery worth contemplating. Current estimates suggest that somewhere in the observable universe, a fast radio burst goes off every few seconds. Think about that for a moment. While you've been listening to these words, dozens or perhaps hundreds of fast radio bursts have occurred somewhere in the cosmos. Most of them we'll never detect, their signals passing by Earth when our telescopes are pointed elsewhere, or too faint by the time they reach us to rise above the cosmic noise. We're catching only the tiniest fraction of these cosmic signals, like trying to understand ocean waves by catching individual drops of spray. This frequency of occurrence raises interesting questions about their origin. If they're natural phenomena, what process could be so common throughout the universe, yet still exotic enough that we don't see it happening in our own galaxy very often? If they're artificial, what would motivate civilizations throughout the cosmos to produce such signals with such frequency? Perhaps it's a kind of cosmic internet, with bursts serving as data packets transmitted between galaxies. Or maybe it's more like a cosmic lighthouse system, with different civilizations maintaining beacons to help others navigate the vast darkness. The technology required to detect fast radio bursts is itself a testament to human ingenuity and patience. Radio telescopes around the world work together in coordinated campaigns, their vast dishes pointed at the sky, listening for whispers from the cosmic deep. The data they collect is measured in petabytes, requiring sophisticated algorithms and powerful computers to sift through, searching for the brief signatures of fast radio bursts hidden in the noise. It's like trying to hear a specific conversation in a crowded stadium, except the conversation lasts only milliseconds and comes from billions of light years away. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, has revolutionized fast radio burst detection. This unusual telescope, which looks more like a series of half-pipes than a traditional dish, can observe vast swathes of the sky simultaneously. Since it began operations, KIME has detected hundreds of fast radio bursts, transforming what was once a rare phenomenon into an almost routine observation. Yet each detection still carries that spark of mystery, that sense of connection with something far beyond our everyday experience. As you lie there, perhaps feeling the gentle pull of sleep beginning to embrace you, consider how remarkable it is that we can even detect these signals. The radio waves from fast radio bursts are stretched by the expansion of the universe itself, their wavelengths growing longer as space expands during their journey to Earth. By the time they reach us, they've been transformed by their passage through cosmic time, carrying information not just about their source, but about the universe they've travelled through. The search for optical counterparts to fast radio bursts has mostly come up empty, adding another layer to the mystery. When a burst occurs, telescopes around the world swing into action, searching for any visible light that might accompany the radio emission. In most cases, they find nothing. No flash of light, no afterglow, just the radio signal itself, pure and enigmatic. It's as if these bursts are designed to be heard but not seen. Cosmic messages transmitted on a single channel that requires specific equipment to detect. This absence of optical emission constrains our theories about what produces fast radio bursts. Many cosmic phenomena that produce powerful radio emissions also produce visible light, X-rays, or gamma rays. Supernovae, for instance, are spectacular across the entire electromagnetic spectrum. The fact that fast radio bursts seem to prefer radio waves, and very specific radio frequencies at that, suggests either a natural process we don't fully understand, or perhaps an intentional choice to broadcast on frequencies that can penetrate cosmic dust and gas. The few cases where optical emission has been tentatively associated with fast radio bursts have only deepened the mystery. In 2020, a fast radio burst was detected from within our own galaxy, from a magnetaire known as SGR 1935+2154. This was accompanied by X-ray emission, providing the first clear link between fast radio bursts and magnetaires. Yet this burst was much weaker than the extragalactic bursts we typically observe, thousands of times less energetic. It's as if we've found a cosmic whisper that might be related to the cosmic shouts we've been hearing, but we're not sure if they're the same phenomenon at different volumes or entirely different types of signals. The implications of fast radio bursts for our understanding of the universe extend beyond their origin. They're becoming tools for cosmology, ways to probe the structure and composition of the universe. The dispersion measure of each burst tells us about the electron density along its path, providing information about the intergalactic medium that we can't easily obtain any other way. It's like having cosmic messengers that not only carry information about their origin, but also map the territory they've travelled through. Some scientists have proposed using fast radio bursts to measure the expansion rate of the universe, to weigh the cosmic web, to search for dark matter. Each burst becomes a cosmic Swiss Army knife, a multi-purpose tool for understanding aspects of the universe that have nothing to do with the burst itself. Whether they're natural or artificial, fast radio bursts are already advancing our understanding of cosmology in ways their discoverers never anticipated. As we approach the deeper parts of our journey tonight, let's take a moment to appreciate the profound nature of what we're contemplating. Every fast radio burst we detect is a bridge across cosmic time. The radio waves that reach our telescopes have been travelling since before our species existed, before our planet had its current continents, before our sun had planets at all. They've crossed distances so vast that light itself, the fastest thing in the universe, needs billions of years to traverse them. And yet, here we are, small beings on a small planet, able to detect and wonder about these cosmic signals. The distribution of fast radio burst sources across cosmic time tells us something about their evolution. We see them from galaxies at various distances, which means various times in cosmic history. Some come from the relatively nearby universe, only hundreds of millions of light years away. Others come from the edge of the observable universe, from epochs when galaxies were young and the cosmos was a very different place. This temporal distribution might hold clues to their origin. Are they more common in the young universe or the old? Do their properties change with cosmic time? These questions guide ongoing observations and theoretical work. The energy source for fast radio bursts remains one of the most challenging aspects of the mystery. To produce such powerful signals, even for milliseconds, requires tapping into enormous energy reserves. Magnetars, with their incredible magnetic fields, are one possibility. The magnetic field energy stored around a magnetar could power thousands of fast radio bursts. But what triggers the release? What determines the timing, the duration, the frequency of emission? These questions remain open, inviting both scientific investigation and imaginative speculation. If fast radio bursts are indeed beacons, we might wonder about the economics of cosmic signaling. Even for an advanced civilization, the energy required to produce such signals would be substantial. What would motivate such expenditure? Perhaps for civilizations that have solved their local energy needs, that have learned to harness the power of their star or even their galaxy, the energy cost of producing fast radio bursts is trivial. Or perhaps the value of cosmic communication, of not being alone in the universe, outweighs any energy cost. The temporal structure of fast radio bursts, the way their intensity changes over those brief milliseconds, contains information we're only beginning to decode. Some show simple profiles, rising and falling smoothly. Others exhibit complex structures, with multiple peaks, valleys, and subpulses. This temporal structure might be telling us about the emission mechanism, about the geometry of the source, about the physics of extreme environments, or it might be carrying encoded information, messages written in the modulation of cosmic signals. As you drift deeper into relaxation, perhaps beginning to lose track of where your body ends and the cosmic contemplation begins, consider the patience required for cosmic communication. If fast radio bursts are beacons, their creators must think on timescales that dwarf human civilization. They must send signals knowing that any response will take millions or billions of years to arrive. It's a kind of cosmic optimism, a faith that intelligence, once emerged, tends to persist, that someone, somewhere, somewhen will be listening. The polarization properties of fast radio bursts continue to surprise astronomers. Some show nearly 100% linear polarization, their radio waves oscillating in perfect alignment. Others show circular polarization, their waves spiraling through space like cosmic corkscrews. The polarization can change during the burst, telling stories about magnetic fields and plasma environments that we're still learning to read. Each burst is like a cosmic poem, written in a language we're only beginning to understand. The search for periodicity in fast radio burst activity has revealed patterns that challenge our understanding. Beyond the obvious repeaters, statistical analyses suggest that even apparently one-off bursts might be part of longer cycles we haven't observed long enough to detect. Perhaps all fast radio bursts repeat, but on timescales ranging from days to centuries to millennia. We've only been watching for a cosmic instant. What patterns might emerge if we could observe a cosmic time? The possibility that fast radio bursts might be associated with gravitational wave events adds another dimension to their mystery. Both phenomena involve extreme physics, massive energy releases, and cosmic distances. While no clear association has been found yet, the search continues. Imagine if fast radio bursts were the electromagnetic counterpart to gravitational wave events. If they were the light that accompanies the ripples in space-time, it would mean that these bursts are connected to some of the most violent and extreme events in the universe. Colliding black holes, merging neutron stars, the birth cries of cosmic monsters. As we prepare to transition into contemplating the vast scales of space where these signals originate, let's rest for a moment in the wonder of our current position. Here we are, on a small planet orbiting an ordinary star, in an unremarkable galaxy among billions, and yet we've developed the ability to detect signals from across the observable universe. We've built instruments sensitive enough to catch whispers from cosmic distances, patient enough to wait for signals that last milliseconds, sophisticated enough to decode information carried across billions of light years. This study of fast radio bursts represents humanity at its best. Our curiosity, our ingenuity, our willingness to contemplate mysteries that have no immediate practical application, but that speak to something deep in our nature. We are the universe becoming aware of itself, as Carl Sagan once said, and fast radio bursts are part of that cosmic self-awareness. Whether they're natural phenomena revealing new physics or artificial beacons announcing cosmic intelligence, they expand our understanding of what's possible in the universe. As we continue our journey into the mystery of fast radio bursts, let's take a moment to truly appreciate the vast scales of space and time we're discussing. When we talk about signals coming from billions of light years away, it's easy for these numbers to become abstract, to lose their meaning in the comfortable darkness where you're resting right now. But these distances, these timescales, they're real, and they're so vast that they challenge our very ability to comprehend them. Yet in attempting to understand these scales, we find a kind of peace, a perspective that makes our daily concerns seem both smaller and somehow more precious. Imagine, if you will, that we could compress the entire history of the universe into a single year, a cosmic calendar where January 1st marks the Big Bang Bang, and tonight, this very moment, is midnight on December 31st. On this scale, our sun and solar system didn't form until early September. Life on Earth didn't appear until sometime in late September or early October. The dinosaurs ruled the Earth for about a week in late December. And humans, our entire species, has existed for only the last few minutes before midnight. The whole of recorded human history, from the first written words to this moment, has taken place in the last 10 seconds of this cosmic year. Now, when we detect a fast radio burst from a galaxy 3 billion light-years away, we're receiving a signal that was sent in late summer of this cosmic calendar, months before our sun even existed. The civilization or natural phenomenon that produced that signal, if it still exists, has experienced 3 billion additional years of evolution, of change, of cosmic history that we know nothing about. They've had 3 billion years to grow, to develop, perhaps to transcend physical existence entirely, or perhaps to fade away, leaving only their signals crossing the cosmos like messages in bottles on an infinite ocean. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, extends about 46 billion light-years in every direction from Earth. This might seem confusing at first, since the universe is only 13.8 billion years old. How can we see things 46 billion light-years away if light has only had 13.8 billion years to travel? The answer lies in the expansion of space itself. While light has been travelling toward us, space has been stretching, carrying distant galaxies even farther away. It's as if we're running on a treadmill that's constantly extending, making our destination recede even as we approach it. Within this vast observable universe, there are an estimated 2 trillion galaxies. 2 trillion. Each galaxy contains hundreds of billions of stars on average. If we could visit 1 star per second, it would take us over 30,000 years just to visit all the stars in our Milky Way galaxy alone. To visit every star in the observable universe at the same rate would take longer than the current age of the universe by a factor of millions. And from any of these countless stars, from any of the planets that might orbit them, fast radio bursts might be emanating, crossing the cosmic void to reach our small world. The spaces between galaxies are not empty, though they might seem that way. These vast voids contain a thin soup of particles, perhaps 1 atom per cubic meter on average. It's a density so low that the best vacuum we can create on Earth is thick by comparison. Yet even this incredibly thin medium affects the fast radio bursts passing through it. Each electron encountered adds a tiny delay to the lower frequency components of the signal, and over billions of light years, these tiny delays add up to measurable dispersion. It's through this dispersion that we can measure the integrated electron density along the burst's path, turning each detection into a probe of the intergalactic medium. When we think about the journey a fast radio burst takes to reach us, we're contemplating a voyage of almost incomprehensible duration and distance. A burst from a galaxy 5 billion light-years away has been travelling since before our solar system formed. During its journey, our sun was born from a collapsing cloud of gas and dust. Planets coalesced from the protoplanetary disk. Earth cooled and developed an atmosphere. Life emerged and evolved from single cells to complex organisms. Continents formed and broke apart. Ice ages came and went. And finally, in just the last cosmic instant, humans developed the technology to detect this ancient signal. The universe through which these signals travel is not static but dynamic, evolving, expanding. When a fast radio burst begins its journey from a distant galaxy, the universe has a certain size, a certain temperature, a certain density. By the time it reaches us, the universe has expanded significantly, cooled further toward its ultimate heat death, and seen the birth and death of billions of stars. The signal itself is a time capsule, preserved in the vacuum of space, carrying information about the universe as it was, not as it is. Consider the loneliness of space through which these signals travel. For most of their journey, fast radio bursts are passing through regions where they might not encounter a single particle for years at a time. They travel through the cosmic voids, those vast bubbles in the large-scale structure of the universe where galaxies are rare and matter is spread impossibly thin. If these signals carry messages, they spend most of their existence in profound isolation, carrying their information through regions where there is literally nothing to observe them, no one to receive them, just the patient continuation of their journey across the expanding cosmos. The cosmic web, that vast network of dark matter filaments that connects galaxies like a three-dimensional spider's web, channels matter and energy throughout the universe. Fast radio bursts must navigate this web, their paths influenced by the gravitational fields of dark matter concentrations we cannot see directly. Sometimes their signals might be gravitationally lensed, bent around massive objects, potentially creating multiple images of the same burst arriving at different times. It's as if the universe itself is playing with these signals, bending and focusing them in ways that add layers to their mystery. When we detect a fast radio burst, we're not just receiving a signal from far away, we're receiving a signal from long ago. This distinction is crucial to understanding the profound nature of these detections. The galaxy that produced a burst billions of years ago might look completely different now. It might have merged with other galaxies. Its stars might have aged and died. New generations of stars might have been born. If the burst was produced by a civilization, that civilization has had billions of years to evolve, to spread throughout their galaxy, perhaps throughout their local group of galaxies. Or they might have disappeared entirely, leaving only their signals as evidence they ever existed. The expansion of the universe affects fast radio bursts in ways that encode information about cosmic history. As space expands, it stretches the wavelengths of the radio waves, causing them to shift toward lower frequencies. This cosmological redshift is like a timestamp, telling us how much the universe has expanded since the signal was emitted. By measuring this redshift, we can determine not just how far away the source is, but when in cosmic history the signal was produced. Each burst carries with it a piece of cosmic history, a snapshot of the universe at a particular moment in its evolution. The rate at which the universe is expanding, described by the Hubble constant, is itself a matter of ongoing scientific debate. Different methods of measuring this expansion rate give slightly different results, a discrepancy that has become known as the Hubble tension. Fast radio bursts offer a potential new way to measure cosmic expansion, independent of other methods. By carefully measuring their dispersion and redshift, astronomers hope to use these signals as cosmic rulers, measuring the expansion of space itself. It's a beautiful example of how mysterious phenomena can become tools for understanding even greater mysteries. As you lie there in the darkness, perhaps feeling yourself floating in that peaceful space between waking and sleeping, imagine yourself as a fast radio burst beginning a journey across the cosmos. You leave your source, whether it's a magneta's violent magnetic storm or an alien beacon's carefully crafted signal, and begin your voyage. Ahead of you stretches billions of years of travel through the cosmic dark. You pass through your host galaxy first, weaving between stars, skimming past planets where life might be emerging or civilizations might be watching the skies. Then you enter intergalactic space, that vast emptiness between galaxies where you might travel for millions of years without encountering anything more substantial than a stray hydrogen atom. During your journey as a fast radio burst, you witness the universe changing around you. Galaxies you pass continue their stately rotation, completing several full rotations during your voyage. You see stars being born in brilliant stellar nurseries, living out their lives, and dying in supernovae explosions that briefly outshine entire galaxies. You pass through galaxy clusters where thousands of galaxies dance together in gravitational harmony, and through cosmic voids where the loneliness of space reaches its ultimate expression. All the while you carry your message, your packet of energy and information, faithfully across the expanding cosmos. The intergalactic medium through which fast radio bursts travel is not uniform but has structure and history. Some regions are enriched with metals from ancient supernovae, stellar explosions that seeded space with elements heavier than hydrogen and helium. Other regions remain pristine, composed of primordial gas that has remained unchanged since the first few minutes after the Big Bang. Each region leaves its mark on passing signals, adding to the dispersion measure, rotating the polarization, subtly altering the burst in ways that encode information about the cosmic environment. The magnetic fields that permeate intergalactic space are incredibly weak, billions of times weaker than Earth's magnetic field, yet they extend over such vast distances that their cumulative effect on fast radio bursts is measurable. These fields can rotate the polarization of the radio waves, an effect called Faraday rotation, which tells us about the magnetic environment along the signal's path. It's as if each burst is a probe, measuring the magnetic fields of regions we could never hope to visit, mapping the magnetic structure of the universe one signal at a time. When we consider the number of fast radio bursts that must be crossing the cosmos at any given moment, the universe becomes a place filled with invisible messages. If bursts occur every few seconds somewhere in the observable universe, then millions of bursts are currently in transit, carrying their energy and information across the cosmic void. Earth is continuously bathed in these signals, most too weak to detect by the time they reach us, others passing by when our telescopes are pointed elsewhere. We're swimming in a sea of cosmic signals, only occasionally catching one in our electromagnetic nets. The host galaxies of fast radio bursts span a remarkable range of distances and cosmic epochs. Some are relatively nearby, only a few 100 million light-years away, close enough that we can study their structure in detail, identifying spiral arms, star-forming regions and galactic nuclei. Others are so distant that they appear as mere smudges of light in our most powerful telescopes, their light stretched and reddened by the expansion of space. Each host galaxy has its own story, its own history of star formation, galactic mergers, and chemical evolution, and somehow, within these diverse environments, the conditions arise to produce fast radio bursts. The distribution of fast radio bursts across the sky appears to be isotropic, meaning they come from all directions equally. This isotropy tells us that the sources are cosmological, not local to our galaxy or even our local group of galaxies. If fast radio bursts were produced within the Milky Way, we would expect to see more of them along the plane of our galaxy, where most stars and stellar phenomena are concentrated. Instead, they come from every direction, from above and below the galactic plane, from every constellation in our sky, as if the entire universe is participating in this cosmic phenomenon. As we contemplate these vast scales, it's natural to feel both humbled and elevated, humbled by our tiny place in such an enormous cosmos, elevated by our ability to detect and begin to understand phenomena occurring at such incredible distances. We are, as far as we know, the only species on Earth capable of contemplating fast radio bursts, of wondering about signals from billions of light years away. In the entire history of life on our planet, Only in the last century have any Earth creatures been able to detect radio waves from space, and only in the last 2 decades have we known about fast radio bursts. The silence between fast radio bursts is as profound as the signals themselves. For every burst we detect, there are vast stretches of time when our telescopes hear nothing but the faint cosmic microwave background and the radio emissions of local sources. This silence isn't empty, but pregnant with possibility. At any moment a burst might arrive, carrying information from cosmic distances, adding another piece to our growing puzzle. The patient astronomers who monitor the cosmos for these signals embody a kind of cosmic meditation, waiting in the silence for whispers from the deep. The technology required to detect fast radio bursts across such vast distances is a testament to human ingenuity. Our radio telescopes must be sensitive enough to detect signals that have been travelling for billions of years, weakened by the inverse square law that dilutes all radiation as it spreads through space. By the time a fast radio burst reaches Earth, its signal is incredibly faint, requiring massive dishes or arrays of antennas to collect enough radio waves to rise above the noise. It's like trying to hear someone whispering from the other side of the observable universe. The computational challenges of detecting fast radio bursts are equally impressive. Modern radio telescopes generate enormous amounts of data, streams of information that must be processed in real time to search for the brief signatures of bursts. Sophisticated algorithms sift through this data, looking for signals that have the right characteristics, the right dispersion measure indicating an extragalactic origin, the right pulse width suggesting a compact source, the right frequency structure distinguishing them from terrestrial interference. It's a needle in a haystack problem, except the haystack is the size of the universe and the needle exists for only milliseconds. As we move deeper into the night, deeper into our contemplation of these cosmic signals, let's consider what it means that we can detect phenomena from such distances. Every fast radio burst we observe is proof that information can travel across cosmic scales, that events in one part of the universe can influence and be observed in another part, even when separated by billions of light years. This cosmic connectivity, this ability for information to propagate across the universe, is fundamental to the possibility of cosmic communication, whether natural or artificial. The redshift of fast radio bursts tells us not just about distance, but about the history of cosmic expansion. As the universe expands, it stretches the wavelengths of all electromagnetic radiation travelling through it. A burst that was emitted at one frequency arrives at Earth at a lower frequency, its waves stretched by the expansion of space itself. This stretching is cumulative, encoding information about the entire expansion history of the universe along the signal's path. It's as if each burst carries with it a record of cosmic expansion, a measurement of how much the universe has grown during its journey. The most distant fast radio bursts detected so far come from redshifts approaching 1, meaning the universe has roughly doubled in size since their signals began their journey. When these bursts were emitted, the universe was hotter, denser, and more active in star formation than it is today. Galaxies were closer together, cosmic structures were still forming, and the first generation of stars might still have been shining. These ancient bursts carry information from a younger, more violent universe, a cosmos in the throes of youth rather than the middle age it has entered now. The intervening galaxies and galaxy clusters that fast radio bursts pass through on their journey to Earth add their own signatures to the signals. Each massive object along the path can gravitationally lens the burst, potentially creating multiple images or amplifying the signal. Each galaxy's halo of hot gas adds to the dispersion measure. Each magnetic field contributes to Faraday rotation. By the time a burst reaches us, it has been modified by its entire journey, carrying information not just about its source, but about everything it has encountered along the way. As you drift in that peaceful space between consciousness and sleep, imagine the universe as a vast ocean, with galaxies as islands scattered across its surface. Fast radio bursts are like waves propagating across this ocean, carrying energy and information from distant shores. Some waves are large and powerful, easily detected as they wash over our cosmic island. Others are faint ripples by the time they reach us, barely distinguishable from the background noise of the cosmic sea. Yet each wave, each burst connects us to distant parts of this ocean, reminding us that we're part of a larger whole. The statistical properties of fast radio bursts are beginning to reveal patterns that might help us understand their origin. The distribution of their energies follows what scientists call a power law, with many weak bursts and fewer strong ones, similar to earthquakes or solar flares. This suggests that whatever process produces them might be scale invariant, working the same way whether producing weak bursts or strong ones. It's a clue to the underlying physics, a hint that might eventually lead us to understand what creates these mysterious signals. The rate at which we discover new fast radio bursts is accelerating, not because they're becoming more common, but because our ability to detect them is improving. New telescopes like CHIME can survey large areas of the sky simultaneously, catching bursts that previous telescopes would have missed. Future telescopes like the Square Kilometre Array will be even more sensitive, potentially detecting thousands of bursts per day. We're on the verge of transitioning from fast radio burst astronomy, where each detection is noteworthy, to fast radio burst cosmology, where we use large populations of bursts to study the universe itself. The story of how humanity first discovered fast radio bursts is itself a meditation on patience, serendipity, and the unexpected ways the universe reveals its secrets to those who listen carefully. It wasn't a discovery made in a moment of dramatic revelation, but rather a quiet realization that emerged from careful analysis of archived data, a whisper from the cosmos that had been waiting patiently in digital storage for someone to notice it. As you settle deeper into comfort, perhaps adjusting your position slightly to find that perfect spot of relaxation, let's journey back to that moment when humanity first heard these impossible signals from the cosmic deep. It was 2007, and Duncan Lorimer, an astronomer at West Virginia University, was working with his student David Narkovich on what seemed like a routine project. They were searching through archival data from the Parkes Radio Telescope in Australia, data that had been collected 6 years earlier in 2001. The Parkes Telescope, a 64-metre dish nestled in the countryside of New South Wales, had been conducting a survey of pulsars, those spinning neutron stars that emit regular radio pulses like cosmic lighthouses. The data they were examining had already been searched for pulsars, but Lorimer thought it might be worth looking again with fresh eyes and updated techniques. As they sifted through the vast streams of data, something unusual caught their attention. There, buried in observations from July 24th, 2001, was a signal unlike anything they expected to find. It was a burst of radio waves that lasted just 5 milliseconds, but its properties were extraordinary. The signal showed a dispersion measure far higher than anything that could be produced within our Milky Way galaxy. If the dispersion was to be believed, this signal had travelled through enough electrons to suggest it came from far beyond our galaxy, perhaps billions of light years away. Yet its intensity was remarkable, briefly outshining all the radio sources in that part of the sky combined. The discovery was so unexpected, so outside the realm of known astronomical phenomena, that Lorimer and his team spent months verifying their finding. They checked and rechecked the data, ruling out instrumental effects, satellite interference, and terrestrial sources. They examined the telescope's logs from that day, looking for any unusual events that might explain the signal. They even considered the possibility that it might be some form of previously unknown interference from Earth, perhaps from a microwave oven in the observatory's break room or a passing aircraft. But every test they performed only strengthened the case that this was a genuine astronomical signal from far beyond our galaxy. The astronomical community's initial response to the discovery was one of healthy skepticism mixed with intense curiosity. Here was a signal that, if real, represented an entirely new class of astronomical phenomena. The energy implied by the burst's intensity and distance was staggering, equivalent to the sun's total output over decades compressed into milliseconds. How could nature produce such an intense, brief signal? What kind of cosmic process could generate radio waves powerful enough to be detected from billions of light years away, yet lasting such a short time that they could easily be missed? This first burst, which came to be known as the Lorimer burst, remained unique for several years. Despite intensive searches through other archival data and dedicated observing campaigns, no other similar bursts were found initially. This uniqueness led some astronomers to wonder if the Lorimer burst might be a fluke, a one-time event that we were lucky to catch, or perhaps unlucky, as it might never be explained. The silence that followed the initial discovery was deafening, each non-detection adding to the mystery and the skepticism. Then, in 2011, astronomer Sarah Burke-Spolaur found something that seemed to cast doubt on the cosmic origin of the Lorimer burst. She discovered signals in Parkes' data that looked similar to the Lorimer burst, but appeared to be coming from all directions at once, suggesting they were local interference rather than cosmic signals. These became known as perytons, named after a mythical creature with the head and wings of an eagle and the body of a deer, a chimera that seemed appropriate for these puzzling signals that appeared celestial but might be terrestrial. The peryton discovery created a crisis of confidence in the fast radio burst field. If these peryton signals, which looked so similar to the Lorimer burst, were terrestrial interference, might the Lorimer burst itself be some form of interference we didn't understand? The small community of astronomers interested in these phenomena found themselves defending the cosmic origin of the Lorimer burst, while acknowledging that similar-looking signals were definitely coming from Earth. It was a challenging time, requiring patience and persistence in the face of mounting skepticism. The mystery of the perytons was eventually solved in 2015 in a discovery that was both mundane and profound. Emily Petroff and her team at Parkes discovered that perytons were indeed terrestrial in origin. They were produced by microwave ovens at the observatory when their doors were opened prematurely, before the heating cycle was complete. The microwaves would emit a brief burst of radio waves that the sensitive telescope could detect. This discovery, while slightly embarrassing, actually strengthened the case for the cosmic origin of the Lorimer burst and other fast radio bursts that had been discovered by then, as they had distinctly different characteristics from the peritons. By 2013, the existence of fast radio bursts as a cosmic phenomenon was firmly established. 4 more bursts had been discovered in Parkes' archival data, each showing the high dispersion measures indicative of extragalactic origin. These discoveries, published by Dan Thornton and colleagues, transformed fast radio bursts from a singular curiosity to a population of events. The statistical analysis of these bursts suggested that they were occurring frequently throughout the universe, perhaps thousands of times per day across the entire sky, but we were only catching the tiniest fraction of them. The discovery of fast radio bursts at other telescopes was crucial for establishing their cosmic nature. In 2014, the Arecibo telescope in Puerto Rico, one of the world's largest radio dishes, until its tragic collapse in 2020, detected a fast radio burst. This detection, made by a completely different instrument in a different part of the world, eliminated any lingering doubts that these signals might be some quirk of the Parkes telescope. Fast radio bursts were real, they were cosmic, and they were happening all around us. The turning point in fast radio burst science came in 2016, with the discovery that at least some fast radio bursts repeat. FRB 121102, first detected in 2012, was observed to produce multiple bursts. This was revolutionary because it immediately ruled out any cataclysmic origin for at least this burst. Whatever was producing FRB 121102 wasn't being destroyed in the process. It could burst again and again, sometimes producing multiple bursts in a single day, then going quiet for weeks or months before bursting again. The repeating nature of FRB 121102 allowed astronomers to do something that had been impossible with one-off bursts: determine its precise location. By monitoring the source with multiple telescopes, including the Very Large Array in New Mexico, astronomers pinpointed the burst to a dwarf galaxy about 3 billion light-years away. This was the first time a fast radio burst had been definitively associated with a host galaxy, transforming them from mysterious signals from somewhere in the cosmos to phenomena we could place in specific cosmic contexts. The host galaxy of FRB 121102 was itself interesting. A small, metal-poor dwarf galaxy with active star formation. This wasn't the kind of galaxy astronomers might have expected. It wasn't a massive elliptical galaxy filled with exotic objects, nor was it a galaxy showing obvious signs of unusual activity. It was a relatively modest galaxy, the kind that exists in vast numbers throughout the universe. This suggested that whatever produces fast radio bursts doesn't require exceptional conditions, that perhaps these signals could come from anywhere. As more fast radio bursts were discovered, patterns began to emerge that deepened the mystery. Some bursts showed complex structure in their brief duration, with multiple peaks and valleys in intensity. Others were simple, single pulses. Some showed frequency structure, with the signal sweeping from high to low frequencies or showing distinct bands of emission. Others were broadband, emitting across a wide range of frequencies simultaneously. This diversity suggested that either there were multiple types of fast radio burst sources or a single type of source that could produce a variety of signals depending on conditions. The discovery of fast radio bursts has required astronomers to develop new observing strategies and technologies. Traditional radio astronomy often involves long observations of specific targets, carefully planned and executed. But fast radio bursts are unpredictable, appearing randomly across the sky, and lasting such a short time that they're usually over before anyone knows they've happened. This has led to the development of new telescopes and observing modes designed to survey large areas of the sky continuously, waiting patiently for bursts to occur. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, represents a new paradigm in fast radio burst detection. Rather than a traditional dish that points at specific targets, CHIME consists of 4 cylindrical reflectors that observe a large strip of the sky simultaneously. As Earth rotates, CHIME surveys the entire northern sky every day. Since beginning operations in 2018, CHIME has detected hundreds of fast radio bursts, transforming what was once a rare phenomenon into an almost routine observation. The CHIME discoveries have revealed new aspects of the fast radio burst phenomenon. Some sources produce bursts with periodic activity, like FRB 180916 with its 16.35-day cycle. Others show no apparent pattern, bursting randomly, or perhaps following patterns too complex or long-term for us to discern yet. CHIME has also discovered bursts at lower radio frequencies than previously observed, expanding our understanding of the frequency range over which these signals can occur. The discovery that some fast radio bursts show periodic activity has profound implications for understanding their origin. FRB 180916's 16.35-day period is remarkably stable, maintained over years of observation. This periodicity might be due to orbital motion in a binary system, with the burst source being eclipsed or somehow modulated by a companion star. Or it might be due to precession of the burst source, like a wobbling top that points toward Earth only at certain times. The stability of the period argues against random processes and suggests an underlying order to at least some fast radio burst sources. In April 2020, a breakthrough discovery linked fast radio bursts to magnetars, at least in one case. SGR 1935 plus 2154, a magnetar in our own galaxy, produced a burst of radio waves that, while much weaker than extragalactic fast radio bursts, had similar characteristics. This was accompanied by X-ray emission, providing the first clear multi-wavelength detection of a fast radio burst-like event. While this burst was thousands of times weaker than typical fast radio bursts, it suggested that at least some fast radio bursts might be produced by magnetars, neutron stars with extreme magnetic fields. The discovery of fast radio bursts has also revealed the importance of archival data in astronomy. The Lorimer burst was hiding in 6-year-old data, waiting to be discovered. This has led to renewed interest in mining archival observations, searching for phenomena that might have been missed or not recognized at the time. It's a reminder that the universe's secrets aren't always revealed in real time, that sometimes discovery requires patience, persistence, and a willingness to look again at what we think we already know. The international nature of fast radio burst research reflects the global character of modern astronomy. Discoveries have been made using telescopes in Australia, Puerto Rico, Canada, the Netherlands, China, and many other countries. Data is shared freely among researchers worldwide, with new detections often announced immediately so that other telescopes can follow up. This collaboration across borders and time zones embodies the idea that cosmic mysteries belong to all humanity, not to any single nation or institution. The role of serendipity in the discovery of fast radio bursts cannot be overstated. Lorimer and Narkovich weren't looking for a new type of cosmic signal when they found the first burst. They were searching for pulsars, well-understood objects that had been studied for decades. The burst appeared in their data unexpectedly, uninvited, challenging their expectations and forcing them to consider possibilities they hadn't imagined. It's a reminder that the universe often reveals its secrets not to those who know exactly what they're looking for, but to those who remain open to surprise. The technological advances that enabled the discovery of fast radio bursts continue to accelerate. New telescopes are being built specifically to detect these signals with unprecedented sensitivity and sky coverage. The Square Kilometre Array, currently under construction in Australia and South Africa, will be able to detect fast radio bursts from even greater distances, perhaps from the edge of the observable universe. Machine learning algorithms are being developed to sift through the vast amounts of data these telescopes produce, identifying bursts in real time and alerting other telescopes for follow-up observations. As you lie there in the peaceful darkness, perhaps feeling your breathing slow and deepen, consider the patience required to discover fast radio bursts. Astronomers spend countless hours observing seemingly empty patches of sky, waiting for signals that might never come. They develop new instruments, write complex software, and analyze vast data sets, all in the hope of catching a few milliseconds of cosmic signal. It's a kind of meditation, this patient watching and waiting, this attention to the subtle whispers of the universe. The discovery of fast radio bursts has changed our understanding of what kinds of signals the universe can produce. Before 2007, no one imagined that such powerful, brief radio signals were constantly flashing across the cosmos. Now we know that the universe is more dynamic, more energetic, more mysterious than we thought. Every few seconds, somewhere in the observable universe, a fast radio burst occurs, briefly outshining entire galaxies in radio waves, then fading back into silence. We live in a universe of constant cosmic fireworks, most of which we never see. The human story behind the discovery of fast radio bursts is one of persistence in the face of skepticism, of careful science overcoming initial doubts, of international collaboration revealing cosmic mysteries. From Duncan Lorimer's first detection to today's routine observations by KIME and other telescopes, the field has grown from a handful of researchers to a global community. Graduate students who were children when the first burst was discovered are now leading their own research programs, pushing the boundaries of what we know about these cosmic signals. The naming convention for fast radio bursts, FRB followed by the date of discovery, creates a kind of cosmic calendar. FRB 010724, the Lorimer burst, marks the beginning of this calendar, though it was discovered years after it occurred. Each subsequent burst adds a new date, a new moment when Earth's telescopes happen to be pointing in the right direction at the right time to catch a cosmic signal. It's a reminder that discovery in astronomy often depends on being in the right place at the right time, with the right instruments and the right people paying attention. The discovery of fast radio bursts has also highlighted the importance of open science and data sharing. The data containing the Lorimer burst was publicly available, allowing Lorimer and his team to make their discovery years after the observation. Many fast radio burst discoveries have been made by researchers who weren't part of the original observing teams, who accessed public data and found signals that others had missed. This openness accelerates discovery and ensures that the universe's secrets are available to all who seek them. As we drift deeper into the mystery of fast radio bursts, we encounter one of their most intriguing aspects, the patterns some of them display. These patterns, emerging from what at first seem like random cosmic static, suggest an underlying order that we're only beginning to perceive, like finding a melody hidden in noise or recognizing a rhythm in what seemed like chaos. The discovery of patterns in fast radio bursts has transformed our understanding of these signals and opened new avenues for speculation about their origin. As you settle into that comfortable space where conscious thought begins to soften and blend with deeper contemplation, let's explore these cosmic patterns and what they might mean. The discovery that some fast radio bursts repeat was revolutionary, fundamentally changing how astronomers thought about these phenomena. Before FRB 121102 was observed to repeat, most theories about fast radio bursts involved cataclysmic events, cosmic catastrophes that destroyed their source, a neutron star collapsing into a black hole, two compact objects merging, a massive stellar explosion. These were the kinds of one-time events that seemed capable of producing such powerful signals. But when FRB 121102 burst again and again, sometimes multiple times in a single day, it became clear that at least some sources could produce multiple bursts without being destroyed. The repeating behavior of FRB 121102 is fascinating in its complexity. Sometimes it produces single bursts, isolated events separated by days or weeks of silence. Other times it enters periods of intense activity, producing dozens of bursts in a matter of hours. The energy of individual bursts varies by factors of thousands, from relatively weak signals barely above the detection threshold to powerful bursts that would be visible from across the observable universe. Yet despite this apparent randomness, statistical analysis reveals underlying patterns, suggestions of order hiding within the chaos. When astronomers analyzed hundreds of bursts from FRB 121102, they found something unexpected, a potential periodicity of about 157 days. During this cycle, the source would be active for about 90 days, producing bursts at irregular intervals, then fall silent for 67 days before the cycle repeated. This wasn't a strict periodicity like the ticking of a clock, but rather a statistical tendency, a preference for bursting during certain phases of the cycle. It was as if the source was breathing, inhaling, and exhaling bursts of radio energy in a cosmic rhythm we could barely perceive. The discovery of FRB 180916 added another layer to the pattern mystery. This source, located in a spiral galaxy only 500 million light-years away, making it one of the nearest known fast radio burst sources, shows a remarkably stable 16.35-day periodicity. For about 4 days, the source can produce bursts, though it doesn't always do so. Then it goes quiet for 12 days before the window of opportunity opens again. This pattern has persisted for years of observation, maintaining its schedule with a precision that rivals mechanical clocks. What could cause such regular patterns in fast radio burst activity? Astronomers have proposed various natural explanations, each with its own elegance and challenges. Perhaps the burst source is in a binary system, orbiting around a companion star. During part of its orbit, the companion might block the burst from reaching Earth, or the interaction between the two objects might trigger burst activity only at certain orbital phases. The 16.35-day period of FRB 180916 could be explained by such an orbital scenario, though the details of how the bursts are produced and modulated remain mysterious. Another possibility is that the patterns arise from precession, the wobbling motion that spinning objects undergo when subjected to external forces. Just as Earth's axis wobbles over thousands of years, causing the precession of the equinoxes, a neutron star or magnetar might precess on much shorter timescales. If the burst emission is beamed, like the beam of a lighthouse, precession could cause the beam to sweep across Earth periodically, explaining the observed patterns. This model is attractive because precession is a well-understood physical phenomenon, though applying it to fast radio burst sources requires assumptions about the emission geometry that we can't yet verify. The patterns in fast radio bursts extend beyond simple periodicity. Some sources show clustering of bursts, periods when multiple bursts occur in rapid succession, followed by longer quiet periods. This clustering might be random, the result of statistical fluctuations, or it might reflect underlying physical processes. Perhaps bursts occur when certain conditions are met, when magnetic field configurations reach critical states, or when material falling onto the source reaches a threshold. The clustering could be telling us about the physics of the emission process, if only we could decode its message. The frequency structure within individual bursts also shows patterns that intrigue astronomers. Some bursts exhibit what's called the sad trombone effect, where the frequency of the signal decreases over the duration of the burst, like a trombone slide moving to lower notes. This frequency drift is remarkably linear in some cases, following mathematical relationships that seem almost too perfect for natural phenomena. Either bursts show more complex frequency patterns, with multiple components at different frequencies, or signals that jump between frequency bands in ways that challenge our understanding of natural emission processes. Subpulses within fast radio bursts add another layer of pattern complexity. Many bursts, when examined at high time resolution, reveal that they're not single pulses but collections of shorter subpulses, each lasting microseconds. These subpulses can show remarkable regularity in their spacing and intensity, creating patterns within patterns. In some cases, the subpulses drift in frequency in coordinated ways, as if they're all part of a larger orchestrated phenomenon. The organization of these subpulses suggests that whatever produces fast radio bursts operates with a level of coherence and coordination that's difficult to explain with simple models. The polarization of fast radio bursts often shows systematic patterns that provide clues about their origin. Many bursts are highly polarized, with their radio waves oscillating in specific orientations. This polarization can change during the burst in regular ways, rotating through angles that follow specific patterns. The Faraday rotation measure, which describes how the polarization rotates due to magnetic fields, can be extreme for some bursts, suggesting passage through incredibly strong and organized magnetic fields. These polarization patterns are like fingerprints, potentially unique identifiers that might eventually allow us to classify different types of burst sources. When we step back and look at the population of fast radio bursts as a whole, larger patterns emerge. The distribution of burst energies follows what scientists call a power law, with many weak bursts and progressively fewer strong ones. This pattern is seen in many natural phenomena, from earthquakes to solar flares to avalanches. It suggests that whatever process produces fast radio bursts operates across a wide range of energy scales, with the same underlying physics governing both weak and strong events. This scale invariance is a hallmark of complex systems operating at critical points, balance between order and chaos. The spatial distribution of fast radio bursts across the sky shows its own patterns, or rather, a notable lack of pattern that is itself informative. Bursts come from all directions with roughly equal probability, showing no preference for the plane of our galaxy or any other special direction. This isotropy strongly suggests that fast radio bursts are cosmological phenomena, originating from throughout the universe rather than from our local cosmic neighborhood. The uniform distribution is what we would expect if sources are scattered randomly throughout space, or perhaps not randomly, but according to patterns we haven't yet recognized. The relationship between fast radio bursts and their host galaxies reveals patterns that might tell us about the conditions necessary for burst production. Some bursts come from the spiral arms of galaxies, regions of active star formation where massive stars are born and die. Others come from galactic centers, where conditions are more extreme and exotic objects more common. Still others come from the outskirts of galaxies, or even from regions with no obvious galaxy at all. This diversity of environments suggests that either fast radio burst sources can form under a wide range of conditions, or there are multiple types of sources that we haven't yet learned to distinguish. As you lie there in the gentle darkness, perhaps feeling yourself floating in that peaceful space between waking and sleeping, consider what it would mean if some of these patterns are intentional. If fast radio bursts are beacons, signals deliberately sent across the cosmos, then patterns would be exactly what we'd expect. A beacon is useless if it can't be distinguished from natural phenomena. Adding patterns, whether simple periodicities or complex sequences, would be a way to mark the signals as artificial, to say, this is not random, someone made this. The 16.35-day periodicity of FRB 180916 is particularly intriguing from this perspective. Why 16.35 days? It's not obviously related to any fundamental physical constant or natural timescale. It's not a simple fraction, or multiple of other periods we see in astronomy. Could it be arbitrary, chosen simply to be distinctive, or might it encode information we haven't yet learned to read? The stability of the period over years of observation suggests whatever maintains it is remarkably consistent, whether it's a natural clock or an artificial schedule. The patterns we observe in fast radio burst might be just the tip of the iceberg. Our observations span only a few years for most sources, a cosmic eye blink. Patterns that repeat on timescale of decades, centuries or longer would be invisible to us. There might be nested patterns, cycle within cycles, that we haven't observed long enough to detect. The universe operates on timescales that dwarf human experience, and fast radio bursts might be participating in cosmic patterns that we've only glimpsed the edges of. Machine learning and artificial intelligence are beginning to reveal patterns in fast radio burst data that human astronomers might have missed. These algorithms can sift through vast amounts of data, identifying subtle correlations and patterns that would be impossible for humans to detect manually. As these tools become more sophisticated, they might reveal new layers of organization in fast radio burst signals, patterns that could provide crucial clues to their origin, or even messages we haven't recognized as such. The search for patterns in fast radio bursts has led to some of the most creative thinking in modern astronomy. Scientists have proposed models involving everything from asteroid belts around neutron stars to alien light sails powered by directed energy beams. While many of these ideas might seem far-fetched, the truth is that fast radio bursts have already proven to be stranger than most astronomers imagined. The universe has surprised us before, and it will undoubtedly surprise us again. The patterns in fast radio bursts might also be telling us something fundamental about the universe itself. If bursts are produced by natural phenomena, their patterns reflect the physics of extreme environments, the behavior of matter and energy under conditions we can't replicate on Earth. They might be teaching us about new states of matter, exotic particles, or physical processes we haven't yet discovered. Every pattern is a clue, a piece of evidence about how the universe works at its most extreme scales. The repetition patterns of fast radio bursts have practical implications for astronomy. Knowing when a source is likely to be active allows astronomers to coordinate observations, pointing multiple telescopes at the source during its active periods. This has led to successful campaigns where bursts have been observed simultaneously at multiple wavelengths, providing much richer information than radio observations alone. The patterns, whether natural or artificial, have become tools for deeper investigation. As we contemplate these patterns tonight, drifting in the space between consciousness and dreams, we might wonder what patterns our own civilization broadcasts to the cosmos. Our radio and television signals, our radar systems, our satellite communications all create patterns of electromagnetic emission that radiate from Earth. To a distant observer with sensitive enough instruments, Earth would appear as a source of patterned radio emission, growing stronger over the past century as our technology has developed. We are, inadvertently, part of the cosmic symphony of signals. The study of patterns in fast radio bursts has revealed the importance of long-term monitoring and patience in astronomy. Some patterns only become apparent after years of observation, emerging slowly from what initially seemed like random events. This requires dedication from astronomers who must secure telescope time, maintain funding, and sustain interest in sources that might be quiet for months at a time. It's a testament to human curiosity and persistence that we continue to watch and wait, accumulating data that might reveal patterns we can't yet imagine. As we venture deeper into the mystery of fast radio bursts, we arrive at perhaps the most profound questions surrounding these cosmic signals. Are they natural phenomena, the result of exotic astrophysics we're only beginning to understand, or could they be something more? Deliberate beacons placed across the cosmos like lighthouses marking safe harbours in the vast ocean of space. This question invites us to explore the boundaries between the natural and the potentially artificial, between what the universe creates on its own and what intelligence might add to the cosmic tapestry. As you rest there in the quiet darkness, perhaps feeling the gentle rhythm of your own breathing, let's explore both possibilities with open minds and peaceful curiosity. The natural explanations for fast radio bursts involve some of the most extreme objects and phenomena in the universe. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, stand as leading candidates. These cosmic monsters, only about 20 kilometers across but containing more mass than our Sun, represent matter in its most compressed state outside of black holes. Their magnetic fields are so powerful that they could dissolve your body from 1,000 kilometers away, pulling apart the very molecules that make you who you are. In such extreme magnetic environments, processes we can barely imagine might naturally produce the powerful radio burst we observe. The physics of magnetars is almost magical in its extremity. Their magnetic fields can crack their own crusts, creating starquakes that release more energy than our sun produces in years. These starquakes might trigger massive magnetic reconnection events, where magnetic field lines snap and reconfigure, releasing enormous amounts of energy in brief bursts. It's like a cosmic lightning strike, but one that could be seen from billions of light years away. The detection of a fast radio burst-like signal from the galactic magnetar SGR 1935 plus 2154 in 2020 provided direct evidence that magnetars can produce such bursts, though the relationship between this relatively weak burst and the powerful extragalactic bursts remains unclear. Neutron star mergers present another natural explanation: cosmic collisions of unimaginable violence. When two neutron stars spiral together and merge, they create conditions that exist nowhere else in the universe. The collision produces gravitational waves that ripple through space-time itself, temperatures that exceed 1 trillion degrees, and magnetic fields that could reshape matter at the subatomic level. Such mergers might produce fast radio bursts as their final cry before forming a black hole, though this would only explain one-off bursts, not the repeaters we've discovered. The environment around supermassive black holes offers another arena where fast radio bursts might naturally occur. These cosmic giants, millions or billions of times more massive than our Sun, lurk at the centers of most galaxies. Matter falling into them forms accretion disks that glow with the light of billions of stars. The magnetic fields threading through these disks, combined with the extreme gravity and rotation near the black hole, create conditions where exotic emission processes might occur. Perhaps fast radio bursts are produced when magnetic field lines anchored in the accretion disk are twisted and snapped by the black hole's rotation, releasing bursts of radio energy that propagate across the cosmos. Young neutron stars fresh from the supernova explosions that created them might produce fast radio bursts through processes we're still discovering. These newborn cosmic corpses spin hundreds of times per second, have surface temperatures of millions of degrees, and generate winds of particles moving at significant fractions of the speed of light. The interaction between these winds and surrounding material, perhaps the remnants of the star that exploded, might create conditions for burst production. As the neutron star ages and slows, the bursts might cease, explaining why we don't see them from older pulsars in our galaxy. Cosmic strings, hypothetical defects in space-time left over from the early universe, offer a more exotic natural explanation. These theoretical objects, thinner than an atomic nucleus but potentially stretching across the observable universe, would contain enormous amounts of energy. If cosmic strings exist and occasionally snap or oscillate, they might produce bursts of radiation, including fast radio bursts. This explanation pushes the boundaries of known physics, but remains within the realm of natural phenomena, albeit ones we've never directly observed. Yet, as we consider these natural explanations, we must also acknowledge their limitations. None perfectly explains all the properties we observe in fast radio bursts. The patterns some show, the specific frequencies they prefer, the way some repeat while others don't, all of these features require increasingly complex natural models that sometimes feel forced. It's as if we're trying to explain a symphony by describing the random collisions of air molecules. Perhaps we're missing something fundamental, or perhaps the explanation lies elsewhere. This brings us to the possibility that haunts and excites astronomers in equal measure. What if some fast radio bursts are artificial? What if they're beacons, deliberately created signals designed to be detected across cosmic distances? This isn't wild speculation, but a possibility that serious scientists have begun to consider, especially for bursts that show properties difficult to explain through natural processes alone. As you drift in that peaceful space between waking and sleeping, let's explore this possibility without fear or skepticism, but with the open curiosity that drives all great discoveries. If an advanced civilization wanted to announce its presence to the cosmos, fast radio bursts would be an elegant solution. They're powerful enough to be detected across billions of light years, brief enough to be energy efficient, and distinctive enough to stand out against natural cosmic noise. The energy requirements, while enormous by human standards, might be trivial for a civilization that has learned to harness the power of stars or black holes. What seems impossible to us might be routine for beings with millions or billions of years of technological development. Consider the engineering challenges of creating a cosmic beacon. It would need to be powerful enough to overcome the inverse square law that weakens all signals as they spread through space. It would need to operate at frequencies that can penetrate cosmic dust and gas. It would need to be distinctive enough to be recognized as artificial, yet simple enough to be detected by civilizations at various technological levels. Fast radio bursts meet all these criteria remarkably well, almost as if they were designed for the purpose. The repeating fast radio bursts are particularly intriguing from this perspective. A beacon that fires only once would be easily missed, but one that repeats increases the chances of detection. The patterns some show, like the 16.35-day periodicity of FAR-B 180916, might be deliberate, chosen to be distinctive and memorable. It's like a cosmic calling card, a pattern that says, "This is not random, someone made this." The stability of these patterns over years of observation suggests a level of control and consistency that nature rarely achieves. The frequency structure of fast radio bursts might encode information we haven't yet learned to read. The sad trombone effect, where frequencies drift in specific ways during the burst, could be a form of frequency modulation carrying data. The subpulses within bursts might be digital packets, each carrying part of a larger message. We might be like someone from the pre-radio era trying to understand a Wi-Fi signal, recognizing that it's structured but lacking the context to decode its meaning. If fast radio bursts are beacons, they might serve various purposes. They could be navigational aids, marking important locations in the galaxy like cosmic lighthouses. They might be memorial signals, created by civilizations to ensure they're remembered long after they're gone. They could be part of a galactic internet, carrying information between civilizations separated by vast distances. Or they might simply be announcements, cosmic "we are here" signals sent out in the hope that someone somewhere will notice. The distribution of fast radio bursts across the cosmos might tell us about the distribution of intelligence in the universe. If they're beacons, their locations mark the homes of advanced civilizations, creating a map of intelligence across space and time. The fact that they come from various types of galaxies at various distances might suggest that intelligence can arise under many different conditions, that the universe is more fertile for consciousness than we've dared to hope. The energy source for artificial fast radio bursts could involve technologies we can barely imagine. Perhaps advanced civilizations have learned to tap the rotational energy of black holes, extracting power from the ergosphere where space-time itself is dragged around the spinning singularity. Maybe they've mastered magnetic reconnection, able to store and release magnetic energy with perfect efficiency. Or perhaps they've discovered energy sources we haven't even theorized, tapping into dark energy or extra dimensions or aspects of physics we haven't yet discovered. The timing of fast radio bursts might be coordinated across cosmic distances. If multiple civilizations are producing beacons, they might synchronize their signals in ways we haven't yet recognized. Patterns that seem random to us might become clear when viewed on longer timescales, or when considering the light travel time between different sources. We might be witnessing a cosmic conversation, with bursts being questions and answers exchanged between civilizations separated by millions of light years. As we contemplate these possibilities, it's important to remember that the universe has surprised us before. Pulsars were initially thought to be artificial because their signals were so regular. Quasars were mysterious for decades before we understood them as active galactic nuclei. The cosmic microwave background was initially dismissed as pigeon droppings in a radio antenna. History teaches us to remain open to possibilities that seem unlikely, to follow the evidence wherever it leads, even if it leads to conclusions that challenge our assumptions about our place in the universe. The search for techno-signatures, signs of technology and astronomical observations, has become a legitimate field of scientific inquiry. Fast radio bursts represent one of the most intriguing subjects for this search. Unlike narrow-band radio signals that SETI traditionally looks for, fast radio bursts are broadband and powerful, characteristics that make them easier to detect but harder to produce naturally. Every new burst we discover adds to our database, potentially bringing us closer to recognizing patterns that might indicate artificial origin. The implications of discovering that fast radio bursts are artificial would be profound beyond measure. It would mean we're not alone, that intelligence has arisen elsewhere and reached levels of technology we can barely imagine. It would mean the universe is not just passively observed, but actively participated in by conscious beings who shape it according to their will. It would transform our understanding of our place in the cosmos, from isolated observers to part of a galactic or even universal community. Yet even if fast radio bursts are entirely natural, they still represent cosmic lighthouses of a sort. They mark the locations of extreme physics, of processes that push the boundaries of what's possible in our universe. They're beacons that guide us toward greater understanding of magnetars, neutron stars, black holes, and perhaps phenomena we haven't yet discovered. Whether natural or artificial, they illuminate the cosmos in ways we're only beginning to appreciate. The debate between natural and artificial explanations for fast radio bursts reflects a deeper question about the nature of the universe itself. Is the cosmos purely the result of natural processes, beautiful but unconscious, operating according to physical laws without purpose or intent? Or has consciousness emerged widely throughout the universe, adding a layer of intentionality to the cosmic tapestry? Fast radio bursts sit at the intersection of these profound questions, offering tantalizing hints but no definitive answers. As you rest there in the peaceful darkness, perhaps feeling yourself beginning to drift towards sleep, consider that the answer might not be either or, but both and. Perhaps most fast radio bursts are natural phenomena, produced by magnetars or other exotic objects. but a fewer artificial beacons hidden among the natural signals. This would be the ultimate cosmic needle in a haystack, requiring us to carefully examine each burst for signs of intentionality. The universe might be showing us both its natural wonders and its intelligent inhabitants, if only we can learn to tell the difference. The study of fast radio bursts has taught us humility about what we don't know. Every answer raises new questions. Every discovery reveals new mysteries. Whether natural or artificial, these signals remind us that the universe is far stranger and more wonderful than our ancestors imagined. We live in a cosmos where millisecond bursts can outshine galaxies, where patterns emerge from chaos, where the line between the natural and the potentially artificial becomes increasingly blurred as our understanding deepens. The future of fast radio burst research promises even greater revelations. New telescopes coming online will detect thousands of bursts, building a statistical database that might reveal patterns invisible in smaller samples. Multi-wavelength observations will provide richer information about burst sources. Machine learning algorithms will sift through data in ways human minds cannot, potentially recognizing signatures of artificial origin or new natural phenomena. We stand at the threshold of discoveries that could fundamentally change our understanding of the universe and our place within it. Whether fast radio bursts are natural wonders or cosmic lighthouses, or perhaps both, they've already succeeded in one crucial respect. They've captured our imagination and drawn our attention to the cosmos in new ways. They've reminded us that the universe still holds mysteries, that there are still discoveries to be made that can surprise and humble us. They've connected us to the vast scales of space and time, making us participants in a cosmic story that began billions of years before Earth existed and will continue billions of years after we're gone. As we prepare to explore what these signals might mean, if they are indeed messages across the void, let's rest for a moment in the wonder of not knowing. There's a peculiar peace in acknowledging mystery, in accepting that the universe holds secrets we haven't yet unraveled. Whether fast radio bursts are the universe's way of showing us new physics, or other intelligence's way of saying hello, they remind us that we're part of something larger, something magnificent, something that invites our curiosity and rewards our patience with glimpses of cosmic truth. As we continue our journey through the cosmic mystery of fast radio bursts, let us now contemplate one of the most profound possibilities that these signals present. What if they are indeed intentional messages deliberately sent across the vast emptiness of space? What would it mean for humanity, for our understanding of our place in the universe, if these brief but powerful signals are attempts at communication from civilizations so distant that their light has been travelling toward us since before our sun was born? As you settle deeper into peaceful contemplation, perhaps feeling the gentle weight of sleep beginning to embrace you, let's explore this possibility with the wonder and openness it deserves, considering what it would mean if we are, in fact, receiving messages across the cosmic void. The concept of interstellar communication has fascinated humanity since we first understood that the stars might harbour other worlds. But the reality of such communication presents challenges that dwarf any engineering feat our species has accomplished. The distances involved are so vast that even light, the fastest thing in the universe, needs years, centuries, millennia, or even billions of years to traverse them. A civilization attempting to communicate across such distances would need to think on timescales that make human history seem like a brief flicker. they would need patience that transcends individual lifetimes, perhaps even transcends the lifetime of their species, planning for conversations where responses might not arrive for millions of years. If fast radio bursts are messages, their senders have solved the fundamental problem of interstellar communication: how to create a signal powerful enough to survive the journey across cosmic distances. Every signal weakens as it spreads through space, following the inverse square law that governs all radiation. A signal that starts with the power of a lighthouse becomes fainter than a candle flame by the time it crosses interstellar distances. To overcome this dilution, the signal must either start with enormous power or be focused into a narrow beam. Fast radio bursts, with their incredible energies, represent one solution to this problem, concentrating enough power into brief pulses that they remain detectable even after journeying for billions of years. Consider the profound loneliness that might drive a civilization to send such messages. Imagine beings who have explored their own solar system, perhaps colonized nearby stars, but still wonder if they are alone in the vast cosmos. The silence of the universe, what scientists call the Fermi paradox, might weigh on them as it weighs on us. Are we alone? Is intelligence a cosmic accident, a one-time fluke in an otherwise unconscious universe? Or are there others out there, separated by such vast distances that communication seems impossible? The creation of cosmic beacons might be an act of hope, a refusal to accept cosmic loneliness, a declaration that says, "We are here, we exist, we want to know we're not alone." The timing of fast radio bursts, if they are messages, might encode information in ways we haven't yet recognized. The intervals between bursts from repeating sources could be a form of temporal coding, with the pattern of gaps carrying meaning. Like Morse code but stretched across cosmic time, the presence and absence of signals might spell out messages for those patient enough to listen and clever enough to decode them. The 16.3 5-day periodicity of FRB 180916, maintained with clockwork precision, might be telling us something specific, if only we knew how to read it. The frequency structure within individual bursts offers another channel for potential information encoding. The way frequencies drift during a burst, the specific frequencies that are emphasized or suppressed, the relationship between different frequency components, all of these could carry data. Advanced civilizations might layer information in their signals with basic patterns to attract attention, and more complex encodings for those sophisticated enough to detect them. It's like a cosmic message with multiple levels of meaning, accessible to civilizations at different stages of technological development. If we imagine the civilizations that might send such messages, we must think beyond our human limitations and biases. These beings might experience time differently than we do, perhaps living for millions of years individually or existing as collective consciousnesses that transcend individual mortality. For such beings, sending messages that take millions of years to reach their destination might seem perfectly reasonable, even quick. They might think in geological or cosmic timescales as naturally as we think in days and years. The energy requirements for producing fast radio bursts, while staggering by human standards, might be trivial for truly advanced civilizations. A civilization that has surrounded its star with a Dyson sphere, capturing all of its energy output, would have power beyond our current comprehension. They might use a fraction of this energy to power beacons. the same way we use a tiny fraction of our electrical grid to power radio transmitters. For them, the energy cost of announcing their presence to the universe might be negligible compared to the potential reward of making contact with other intelligences. The choice of radio frequencies for these hypothetical messages is itself interesting. Radio waves can penetrate cosmic dust and gas that would block visible light. They can travel across intergalactic distances without being absorbed. They're relatively easy to generate and detect, requiring technology that any civilization capable of astronomy would likely develop. If you wanted to send a message that had the best chance of being received by the widest possible audience of technological civilizations, radio waves would be an excellent choice. The possibility that fast radio bursts might be something like a galactic internet adds another layer to their mystery. Perhaps these aren't messages aimed at us specifically, but rather communications between advanced civilizations that we're inadvertently intercepting. Like picking up fragments of conversations on a radio scanner, we might be detecting signals not meant for us, but revealing nonetheless that we're not alone. The repeating nature of some sources might represent regular data transmissions, updates sent between distant outposts of a galactic civilization. The content of these hypothetical messages, if we could decode them, might be beyond our current ability to understand. A civilization millions of years ahead of us might have concepts, mathematics, and ways of organizing information that we can't yet comprehend. It would be like trying to explain quantum mechanics to a medieval scholar. The conceptual framework simply doesn't exist. Yet the attempt to communicate suggests a belief that intelligence, wherever it arises, shares certain universal qualities, that mathematics and physics provide a common language that transcends species and cultures. As you drift in that peaceful space between waking and sleeping, imagine the profound optimism required to send messages across cosmic distances. The senders must believe that intelligence, once it emerges, tends to persist and develop. They must have faith that somewhere, somewhen, their signals will be detected and understood. It's a cosmic act of faith, a belief in the universality of curiosity and the drive to explore and understand. These hypothetical beacon builders are saying not just, "We are here," but also, "We believe you are there, whoever you are, whenever you are." The distribution of fast radio burst sources across the cosmos might map the distribution of intelligent civilizations throughout space and time. If these are beacons, then each source marks a place and time where intelligence arose and reached sufficient technological sophistication to announce its presence. The fact that bursts come from various types of galaxies at various distances might tell us that intelligence is not restricted to specific cosmic environments, that consciousness can emerge under a wide range of conditions. The apparent isotropy of fast radio bursts, their even distribution across the sky, might have different implications if they're artificial rather than natural. If natural, it simply means the conditions for their production exist throughout the universe. But if artificial, it might suggest a coordinated effort, a galactic or intergalactic community that has agreed to maintain beacons for the benefit of emerging civilizations. It's a beautiful thought that advanced civilizations might cooperate to create a network of signals saying, "You're not alone," to anyone capable of listening. The challenge of confirming whether fast radio bursts carry messages is immense. We would need to identify patterns that couldn't arise naturally, structures in the data that require intelligence to explain. This is complicated by our limited understanding of what natural processes can produce. Every time we think we've found something that must be artificial, like the regular pulses of pulsars, we discover it's a natural phenomenon we hadn't imagined. The universe is remarkably creative in producing patterns and structures that can mimic what we expect from intelligence. Statistical analysis of fast radio bursts might eventually reveal signatures of artificial origin. If some bursts are natural and others artificial, there should be statistical differences between the two populations. The artificial ones might show less variation in certain parameters, more precise timing, or frequency structures that don't match what we expect from natural processes. As our sample size grows from hundreds to thousands to millions of bursts, these statistical signatures might become apparent. The search for correlated bursts from different sources could provide evidence for coordinated signaling. If multiple sources produce bursts at coordinated times, accounting for the light travel time between them, it would strongly suggest intentional timing. Imagine a network of beacons that fire in sequence, creating a pattern that sweeps across the galaxy like a wave. Such coordination would be nearly impossible to explain through natural processes, but would make perfect sense for a network of artificial beacons. The possibility that we might be receiving messages we can't yet decode is both frustrating and exciting. We might be like early humans finding a smartphone, recognizing it as something special, but lacking the context to understand its purpose or operation. The signals might be there, the messages might be clear to those with the right knowledge, but we're still developing the conceptual framework needed to recognize and interpret them. Every burst we detect and record might be valuable data for future generations, who will have better tools and deeper understanding. The ethical implications of receiving messages from advanced civilizations are profound. If fast radio bursts are attempts at communication, do we have an obligation to respond? Should we announce our presence to the cosmos, potentially inviting contact with civilizations whose intentions we can't know? These questions move from science fiction to serious consideration if we confirm that even one fast radio burst is artificial. The decision of whether and how to respond would be one of the most important our species has ever faced. The psychological impact of confirming that fast radio bursts are messages would transform human civilization. Every burst detection would be headline news, analyzed for potential meaning. The knowledge that we're receiving messages from across the cosmos, even if we can't understand them, would fundamentally change how we see ourselves and our place in the universe. We would no longer be alone, even if the messengers are too far away for practical communication. The cosmic silence would be broken, replaced by a chorus of signals we're only beginning to hear. The possibility that fast radio bursts might contain warnings adds a sobering dimension to their mystery. Advanced civilizations might use beacons to warn others about cosmic dangers, from gamma-ray bursts to expanding regions of space hostile to life. They might be trying to share crucial information about surviving technological adolescence, about avoiding the pitfalls that destroy young civilizations. If so, our inability to decode these messages might mean we're missing vital information about our own survival. The time delay inherent in cosmic communication means that the civilizations sending these messages, if that's what they are, might no longer exist. We might be receiving messages from ghosts, signals from civilizations that flourished billions of years ago, but have since disappeared. This adds a poignant quality to the signals, making them not just messages but memorials, ensuring that these civilizations are remembered even after they're gone. Every burst might be a voice from the past, a cosmic fossil preserving evidence of intelligence that once was. As we contemplate these possibilities, it's worth considering what messages we might send if we had the capability. What would humanity want to say to the cosmos? Would we send mathematical constants proving our intelligence? Would we transmit our music, our art, our stories? Would we warn about the dangers we've discovered or celebrate the beauty we've found? The challenge of deciding what to say to unknown listeners across cosmic distances reveals the difficulty of interpreting messages from others who face the same challenge. The frequency with which fast radio bursts occur suggests that if they are messages, the universe is full of voices calling out. Every few seconds, somewhere in the observable universe, a burst occurs. If even a small fraction of these are artificial, it means thousands of civilizations are actively signaling. The cosmos becomes not a silent void, but a bustling community where distance prevents easy conversation but not the attempt to communicate. We're potentially surrounded by a galactic society we're only beginning to perceive. The evolution of fast radio burst signals over cosmic time might tell us about the evolution of the civilizations producing them, if they are indeed artificial. Bursts from the early universe, when galaxies were young and forming stars rapidly, might represent early attempts at cosmic communication. More recent bursts might show technological advancement, more sophisticated encoding, more efficient energy use. We might be witnessing not just communication, but the technological evolution of cosmic civilizations over billions of years. The polarization of fast radio bursts might carry information in ways we haven't yet explored. Polarization can be controlled precisely, offering another channel for encoding data. The way polarization changes during a burst, the relationship between different polarization states, the patterns that emerge when we analyze polarization across multiple bursts, all of these might contain messages waiting to be decoded. It's like having a book written in a language we don't understand, knowing it might contain profound truths but lacking the key to translation. As you rest there in the darkness, perhaps feeling yourself drifting closer to sleep, consider the profound patience required for cosmic communication. If civilizations are sending messages via fast radio bursts, they're engaging in the ultimate long-term project. They send signals knowing that any response will take millions or billions of years to arrive. They must have a view of existence that transcends individual lives, perhaps even individual species, seeing themselves as part of a cosmic community that operates on geological and cosmic timescales. The possibility that fast radio bursts might be distress signals adds another dimension to their mystery. Perhaps civilizations facing existential threats, from supernovae to gamma-ray bursts to their own technological mistakes, send out final messages to warn others or simply to say, "We were here." These might be the last words of dying civilizations, preserved in radio waves that continue across the cosmos long after their creators are gone. Every burst might be a cosmic epitaph, a final statement from intelligence that briefly flowered in the universe. The role of artificial intelligence in creating and interpreting these signals deserves consideration. Advanced civilizations might have long ago transcended biological intelligence, existing as vast computational networks that think in ways we can't imagine. For such beings, creating and maintaining beacon networks might be trivial, and encoding complex information in brief bursts might be natural. Similarly, our own AI systems might eventually recognize patterns in fast radio burst data that human minds can't perceive, serving as translators for cosmic messages. The possibility that fast radio bursts might be test signals is intriguing. Just as we test our communication systems with specific patterns and signals, advanced civilizations might use fast radio bursts to test their own cosmic communication networks. We might be detecting the equivalent of testing 1, 2, 3 broadcast with the power of stars. These test signals might be deliberately simple, designed to be easily recognized as artificial, while the actual communication happens through channels we haven't yet discovered. Chapter 7: The Architecture of Cosmic Communication. As we delve deeper into the enigma of fast radio bursts and their potential role as cosmic beacons, we must contemplate the vast engineering challenges and philosophical implications of establishing communication across the universe. How might beings engineer signals capable of crossing billions of light years? What kind of patience and perspective would be required to engage in conversations where responses take longer than the lifetime of civilizations? As you lie there in the gentle embrace of approaching sleep, let's explore the architecture of cosmic communication, the infrastructure and intentions that might underlie a universe where intelligence reaches out across the void, seeking connection despite the vast distances that separate us. The engineering requirements for producing fast radio bursts as intentional signals would represent achievements far beyond current human capability, yet perhaps trivial for civilizations with millions or billions of years of technological development. Consider what it would take to generate a burst of radio waves powerful enough to be detected across billions of light years. The energy involved is staggering, equivalent to what our sun produces over decades or even centuries, compressed into milliseconds. Yet for a civilization that has learned to harness the energy of stars, black holes, or perhaps even more exotic sources we haven't yet imagined, such energy expenditure might be routine, like using a flashlight is for us. One possibility that astronomers and physicists have considered is that advanced civilizations might use stellar engines to power their beacons. A stellar engine is a hypothetical megastructure that could extract energy from a star on a massive scale. The simplest version might be a partial Dyson sphere, a swarm of satellites surrounding a star to capture its energy output. More exotic proposals include devices that could extract energy from a star's rotation or magnetic field, or even manipulate stellar evolution to release energy in controlled bursts. With such technology, a civilization could power beacons that would be visible across cosmic distances. The Shkadov thruster, a type of stellar engine proposed by physicist Leonid Shkadov, offers an interesting model for how civilizations might create directed signals. This hypothetical device would use a massive mirror to reflect a star's radiation in one direction, simultaneously propelling the star through space and creating a powerful directed beam. If modulated correctly, such a beam could serve as both a propulsion system and a communication device, allowing a civilization to travel through the galaxy while announcing its presence to anyone in the beam's path. Black holes present another potential power source for cosmic beacons. The physics around black holes is extreme enough to naturally produce powerful emissions, and a sufficiently advanced civilization might learn to harness and control these processes. The ergosphere of a rotating black hole, the region where space-time itself is dragged around the black hole, contains enormous amounts of extractable energy. The Penrose process, a theoretical mechanism for extracting this energy, could power beacons visible across the observable universe. A civilization that has mastered black hole engineering would have essentially unlimited energy for cosmic communication. The placement of beacons throughout the galaxy or across intergalactic space would require thinking on scales that dwarf human experience. If fast radio bursts are indeed beacons, their creators might have engaged in projects lasting millions of years, placing transmitters at strategic locations throughout their galaxy or even beyond. These beacons might mark important locations, habitable zones around stars, stable Lagrange points in stellar systems, the edges of dangerous regions like black holes or neutron stars. They might form a navigation network, a cosmic GPS system for civilizations capable of interstellar travel. The synchronization of beacons across cosmic distances presents fascinating challenges and possibilities. If multiple beacons are coordinated, they must account for the finite speed of light. A signal to synchronize beacons separated by 1,000,000 light-years would take 1,000,000 years to propagate. Yet the remarkable periodicity of some fast radio bursts suggests precise timing maintained over long periods. This might require atomic clocks of extraordinary stability, or perhaps synchronization with natural cosmic clocks like pulsar signals that can be observed from vast distances. Consider the possibility of a galactic internet, a network of beacons and receivers that allows communication between civilizations separated by thousands or millions of light years. Such a network would operate on timescales that make human internet latency seem instantaneous. A query sent across the galaxy might not receive a response for hundreds of thousands of years. Yet for civilizations that think in geological or cosmic timescales, such delays might be acceptable. They might maintain databases and information repositories updated over millennia, creating a slowly evolving collective knowledge base for all participating civilizations. The modulation techniques used in fast radio bursts, if they are indeed engineered signals, might represent communication strategies we haven't yet imagined. The brief duration of bursts might be intentional, concentrating information into packets that can pierce through cosmic noise. The frequency sweeps observed in many bursts might encode data in the rate and pattern of frequency change. The polarization might carry additional information channels. Advanced civilizations might layer information in ways that make efficient use of every aspect of the signal, encoding multiple messages for recipients at different technological levels. The concept of self-replicating beacon probes adds another dimension to cosmic communication architecture. Instead of building individual beacons, an advanced civilization might create von Neumann probes, self-replicating machines that spread throughout the galaxy, establishing beacons as they go. These probes would use local resources to build copies of themselves and new beacons, exponentially expanding the communication network. Over millions of years, such probes could establish beacons throughout a galaxy, creating a comprehensive communication infrastructure without requiring the original civilization to visit each location. The maintenance of beacon networks over cosmic timescales would require extraordinary reliability and redundancy. Components would need to function for millions or billions of years, self-repairing and adapting to changing conditions. The beacons might use multiple power sources, switching between them as stars evolve and die. They might be designed to survive supernovae, gamma-ray bursts, and other cosmic catastrophes. The engineering philosophy would need to account for contingencies on time scales that dwarf the entire history of technology on Earth. As you drift in that peaceful space between consciousness and sleep, imagine the kind of civilization that would undertake such projects. They would need to have solved their immediate survival challenges, overcome the existential risks that threaten young technological species. They would need social stability lasting millions of years, or perhaps have transcended individual mortality, existing as collective consciousnesses or artificial intelligences that can maintain purpose across cosmic time. Their motivations might be as alien to us as their technology, driven by philosophies and goals we can't yet comprehend. The economics of cosmic communication, if we can even apply such concepts to advanced civilizations, might be fundamentally different from anything we understand. For beings with effectively unlimited energy and resources, the cost of maintaining beacon networks might be negligible, or perhaps the value they place on communication, on not being alone in the universe, outweighs any cost. They might see beacon maintenance as a fundamental responsibility of intelligent species, a cosmic duty to help others know they're not alone. The possibility of quantum communication adds a speculative but intriguing element to cosmic communication architecture. While our current understanding of quantum mechanics suggests that faster-than-light communication is impossible, advanced civilizations might have discovered aspects of physics we don't yet understand. They might use quantum entanglement in ways we haven't imagined, or exploit other quantum phenomena to enhance their communication capabilities. Fast radio bursts might be just the classical component of a more complex communication system that includes quantum channels we can't yet detect. The redundancy built into cosmic communication systems might explain some patterns we observe in fast radio bursts. If beacons are designed to ensure message delivery despite cosmic interference, they might repeat signals multiple times with slight variations. The clustering of bursts from some sources might represent error correction protocols, ensuring that even if some bursts are absorbed or distorted during their journey, the message still gets through. The variety in burst properties might not be random, but rather different encoding schemes for different types of information or different intended recipients. The concept of directed versus omnidirectional beacons has important implications for fast radio burst observations. Omnidirectional beacons broadcast in all directions, ensuring maximum coverage but requiring enormous energy. Directed beacons focus their energy in specific directions, achieving greater range with less power but limiting their audience. The fast radio bursts we detect might be a mixture of both types, with some civilizations choosing broad coverage and others targeting specific regions of space where they expect intelligent life to emerge. The evolution of beacon technology over cosmic time might be reflected in the properties of fast radio bursts from different cosmic epochs. Early beacons might be crude and energy inefficient, producing powerful but simple signals. As civilizations advance, their beacons might become more sophisticated, encoding more information in subtler ways. The fast radio bursts we observe from billions of years ago might represent early attempts at cosmic communication, while more recent bursts might employ advanced techniques we haven't yet learned to recognize. The possibility of mobile beacons adds another layer to the architecture of cosmic communication. Instead of fixed installations, some beacons might be mounted on spacecraft or other mobile platforms, traveling through the galaxy while broadcasting. This would explain why some fast radio burst sources seem to appear and disappear. They might be beacons on vessels passing through our observable region. These mobile beacons might serve as scouts, exploring the galaxy while announcing the presence of their creators. The coordination between different types of cosmic signals might be part of a larger communication strategy. Fast radio bursts might be just one component of a multi-wavelength communication system. Advanced civilizations might use different types of signals for different purposes: radio bursts for long-distance announcements, optical lasers for high-bandwidth communication, gravitational waves for signals that need to penetrate dense regions of space. We might be detecting only one channel of a much richer communication network. The philosophy underlying cosmic communication architecture might emphasize resilience and longevity over efficiency. Unlike human communication systems that prioritize speed and bandwidth, cosmic beacons might be designed to survive and function for geological timescales. They might use simple, robust technologies rather than cutting-edge systems that might fail over time. The signals might be deliberately simple to ensure they can be detected and understood by civilizations at various technological levels. The possibility of adaptive beacons that modify their signals based on detected responses is intriguing. If a beacon detects radio emissions from a developing civilization, it might adjust its signals to be more easily detected by that civilization's technology. This would require sophisticated sensors and decision-making capabilities, essentially making each beacon an intelligent agent capable of optimizing its communication strategy. Some variations in fast radio burst properties might represent beacons adapting to perceived audiences. The infrastructure required to support a galactic communication network would be vast beyond imagination. Beyond the beacons themselves, there might be relay stations to boost signals across extragalactic distances, processing centers to decode and route messages, and archives to store information for retrieval by future civilizations. This infrastructure might be largely invisible to us, operating on wavelengths we don't monitor or using technologies we haven't discovered. Fast radio bursts might be just the tip of an enormous iceberg of cosmic communication infrastructure. The sociological implications of maintaining cosmic beacons for millions of years are profound. What kind of society could maintain such long-term projects? They might have social structures utterly unlike anything in human history, with institutions designed to persist for cosmic timescales. They might have solved the problem of institutional decay that affects human organizations, finding ways to maintain purpose and efficiency across millions of years. Or perhaps they've transcended biological evolution entirely, becoming stable artificial intelligences that can maintain consistent goals indefinitely. The possibility that beacon networks might be archaeological artifacts of extinct civilizations adds a poignant dimension to their study. Just as we find ancient ruins on Earth that outlast their creators, cosmic beacons might continue functioning long after the civilizations that built them have disappeared. These automatic systems might be the only evidence that these civilizations ever existed, their final legacy to the universe. Every fast radio burst might be a message from the dead, a voice from a civilization that flourished millions or billions of years ago. The energy harvesting techniques that might power cosmic beacons could teach us about sustainable technology on cosmic scales. If beacons operate for millions of years, they must use renewable energy sources that don't deplete over time. They might harvest energy from cosmic rays, magnetic fields, or the cosmic microwave background. They might use the temperature differential between space and warm objects to generate power. These technologies, if we could understand them, might solve Earth's energy challenges and enable our own ventures into cosmic communication. The decision-making algorithms that govern beacon operation might represent forms of artificial intelligence far beyond our current understanding. These systems would need to operate autonomously for millions of years, making decisions about when to transmit, how to adapt to changing conditions, and how to respond to potential signals from other civilizations. They might embody ethical frameworks and decision-making principles that reflect the values of their creators, preserved in silicon and transmitted across cosmic time. As you continue to drift towards sleep, consider the profound optimism embedded in the architecture of cosmic communication. Every beacon, every signal, every attempt to communicate across the vast distances of space represents a belief that communication is possible, that intelligence elsewhere will eventually develop the capability to detect and respond to these signals. It's an investment in a future that the beacon builders might never see, a gift to civilizations that don't yet exist, a bridge across time and space built on hope and curiosity. The architecture of cosmic communication might include safeguards against misuse or misunderstanding. Advanced civilizations might encode warnings about dangerous technologies or regions of space. They might include "do not reply" messages if they've learned that contact between civilizations at different developmental stages is harmful. The signals might include tests or puzzles that ensure only civilizations with certain capabilities or ethical development can decode the full messages. Fast radio bursts might be just the first layer of a multi-layered communication protocol designed to protect both senders and receivers. The possibility of communication networks that span multiple universes, if such things exist, pushes the boundaries of speculation, but remains within the realm of theoretical possibility. If advanced civilizations have discovered ways to access parallel universes or higher dimensions, fast radio bursts might be leakage from inter-universal communication systems. We might be detecting echoes of signals intended for entirely different realities, glimpses of a cosmic communication network that extends beyond our observable universe.